In addition to geometry and Mach number, compressible flow calculation also depends on a second dimensionless parameter, the specific height ratio. The most important, in addition to geometry and Mach number, compressible flow calculation depends on a second dimensionless parameter, the specific heat ratio. In the previous chapter, we used the same symbol K to denote the thermal conductivity of flow. We apologize for the duplication. Thermal conductivity does not appear in this chapter, so K is the specific ratio in this chapter. Recall the previous chapter. Variation in K have only a slight effect on compressible flow computation, and for air the specific ratio is approximately equals to 1.4. Is the dominant fluid of interest. Therefore, although we assign some problem involving other gas like steam and carbon dioxide CO2 and helium, the compressible flow tables are available in this chapter are based solely on the single value for A. For other gases, we can also use the tables in Appendix P in the reference. The next subsection in this section is the real gas, perfect gas assumption. The perfect gas in principle compressible flow calculations can be made for any fluid equation of states, and we shall assign problems involving the steam tables, the gas tables, and liquids, but in fact most elementary treatments are confined to the perfect gas with a constant specific heat ratio, constant P equals to and we have the specific heat ratio for any fluid. For air this is 1.4. For all real gases, let me write for all, it is for perfect gas. for our real gas. Let me CPCV and K is a function of vary with temperature but only moderately. For example, Cp of air increases 30% as temperature increases. For air, Cp increases 30 with temperature increases. Since we rarely deal with such large temperature change, it is quite reasonable to assume constant specific heats. From the previous chapter, recall the previous chapter, the gas constant is related to universal constant gamma divided by the gas molecular weight, the gas constant. On the molecular weight let be universal constant and the gas molecular weight. Where for the universal gamma equals to or in the SI units we have this quantity for gamma kilomole Kelvin on joule on kilomole Kelvin. And for air, as we know, the molecular weight is and we shall adopt the following property value of air throughout this chapter. For air, we can calculate the properties based on the universal and molecular weight R equals to Rankine, or in SI we have second square K and K specific ratio we now CP R on minus 1 as same as R dimension or in SI units as same as and CV for the A. Experimental value of K for the 8 common gases also available in the chapter figure 1.5 in the chapter. The change in the internal energy U and enthalpy H of a perfect gas are computed for the constant specific heats such as this relation. Let me write secretly the change in the internal energy U and the enthalpy H will be derived as in the perfect gas, for example, delta U change in internal energy U2 minus U1 CV, and for the enthalpy we have also relation for perfect gas, very useful relations in the